Okay, so today is Causal Day, it seems like. So what I noticed yesterday in the talks was, I think in 3 of the 4 talks, people got into causal methods. Everybody was talking about causal methods at some point. And, you know, when we're thinking about medicine and health, we're interested in causes, right? We're not interested in spurious associations. And in biology, we're interested in mechanisms. We're interested in how biological systems work. And that's intimately related to causal approaches as well. So I think in both biology and medicine, causal inferences are key. And I'm really pleased that we've got some great speakers on this topic. And we had to adjust the schedule a bit because Danielle Belgrade couldn't make it, unfortunately. But a good thing is that Matt Sperrin can go first now, and that's good because I think Matt is really going to give some preparatory sort of stuff on causal inference. And Matt's team actually put risk prediction models into production in healthcare systems. So a lot of people talk about prediction models, lots of people publish prediction models, I'm sure I've published prediction models. Very few of those go into production and are actually used in the real world in healthcare systems. Matt actually does this for real, so he has to deal with the real nitty-gritty of risk prediction, and it's a thorny and difficult area. And more recently, people thinking about risk prediction have started thinking about causality, including Matt.
Yeah, so I'll give an introduction to causal inference. And then I guess a bit more of the substance of some of what I'm interested in. So I come from a prediction modelling background originally. I'm a statistician, so I tend to build fairly simple statistical models rather than some of the more advanced machine learning models that some of the other speakers will be telling you about later on. But I'll tell you a bit about why I think and why other people think causal inference is so useful in prediction, regardless of what kind of modelling approach you're using, and then talk a little bit as well about how we combine causal inference with prediction. So I'm based here in Manchester. My background is in statistics, and I originally started out, as Magnus was saying, building prediction models. But one of the things that I sort of learned from going through the process of developing, validating, and deploying these models is really that the way that they get used. We'll come on to this later, but essentially, users of these models behave as if they were causal models, even though they aren't. So it is quite. Maybe it's a connection. Let's check. So yeah, so that sort of motivates what got me into causal inference. So there's a really cool paper that I'd recommend that anybody reads. Which is by Miguel Hernan, that I'm sure many of you have heard of. He's quite a big name in causal inference. A second chance to get causal inference right, a classification of data science tasks. And in this paper, the authors essentially lay out that whenever we're doing data science, and particularly statistics, machine learning, we're typically doing one of 3 things, or sometimes more than one of these 3 things. So the first one being description. So this is sort of your basic exploratory and descriptive analysis. So where we're just trying to provide some sort of summary of a complex data set, or provide some information about the real world. So during COVID, for example, this is what. In various countries, we had all these briefings saying, this is the trajectory of COVID so far, and this has been the number of cases and all this sort of thing. So that's one example where sort of description from data science really made it into the public eye on essentially a daily basis. Then second is prediction. So this is what I guess is the sort of raison d'etre of supervised learning. So we have some input variables, and we're trying to estimate the value of some output variables. So this is just your sort of standard supervised learning type problem. And then the third category is called in this paper counterfactual prediction, but what's really meant, I suppose, is causal inference. So this is not just mapping inputs to outputs, it's essentially mapping hypothetical inputs to outputs. So it's asking questions, if the world had been different, what would be the implications for the outputs that we're interested in? So, if we propose an intervention on some of the inputs, what's the implications for the outputs? And that is a much, much harder problem than simply mapping inputs to outputs. So again, if we just stick with the COVID example for now, prediction, so this is where we sort of predicted forward, how many cases are there going to be tomorrow, next week, and things like that. But this counterfactual prediction, this was the harder question that policymakers and modelers were trying to answer when they propose various population-level interventions, vaccination programs, this sort of thing. So, so this third question is much, much harder and requires a much deeper understanding of the structure of the relationships between variables and the sort of science and mechanisms involved in a problem. So that's all I wanted to say about those three areas, but you certainly find if you read any paper, certainly in the medical and epidemiology literature, if you pick a random paper, I'd say you've probably got at least a 50% chance that the authors are just not clear on which one of those three tasks they're doing, which is quite shocking, really. So it's quite key to think about this. Okay, so by the way, feel free to shout out if you have any questions at any point, although I will try and leave 10 minutes or so at the end for questions. So now I'm going to talk for a while at a fairly introductory level about causal inference. So we'll start off simple and build up, not too much sort of, it's early in the morning, so not too many complicated equations and proofs and technical details. I'm sure you'll have plenty of that later on today. So the way that many people, including me, like to think about causal inference is to think of it in terms of DAGs. So I guess you all know what a DAG is in general, as a graph with nodes and edges, with the key distinction between, if you like, a normal DAG here being that the arrows represent, in some sense, that we'll try and get a bit more specific about a flow of causality, rather than simply a lack of conditional independence, as is often the case in the standard DAG. So the direction of the arrows is absolutely critical here. So the arrow from L to A in this diagram is strictly saying that the variable L causes the variable A and not the other way around. So this is about the simplest DAG that you could draw that is interesting in any way. So three variables. We have L, which I'm sure so we have L, which here you could imagine is obesity. A is a treatment of some kind, saying metformin, and Y is cancer incidence. And the question of interest is whether metformin causes cancer incidence. And by causes, we can mean in either direction. Does taking metformin increase the risk of cancer, or does it decrease the risk of cancer? And I think the jury is still out on that. As far as I know, it's quite a complicated question. But if we can draw a DAG that looks like that, the question, for pedagogical purposes, becomes quite simple. So we're interested in this horizontal arrow going across the bottom from A to Y, and if you have sort of any intuition or background in this area, you'll see that the variable L causes us something of a problem and is acting as a confounder. So straightforward so far, hopefully. I quite like to draw DAGs with time going from left to right. That makes them a lot easier to read, I think. So if time goes from left to right, then unless you have some very strange beliefs about physics, arrows also go from left to right, so causality flows 50 seconds early. Is that okay, Magnus? Okay, so time goes from left to right, and therefore the arrows representing causality go from left to right, because a sort of starting, very sort of basic low-level assumption that we would make is that the flow of causality goes forwards in time. Just to say, so references at the end, but some of these are hyperlinks. So I presume we'll share the slides, Magnus. Yeah, so a lot of these are clickable. But yeah, there's a really good new text by Miguel Hanan and Jamie Robbins for learning about causal inference. So if we just do one sort of slightly philosophical slide, so if you think about it, talk about what we mean by one variable causing another is actually not straightforward at all. And I'm sure you could do a whole people do whole PhDs on philosophy on this sort of question. So we won't dwell too much on this, but going back to Hume, so he said, what does it mean for one thing to cause another? So Hume said, where if the first object had not been, the second never had existed. So that's capturing, on some level, the idea of a counterfactual world. So for the first object to cause the second, what we mean is, if we observe the first object and then the second object, then if you like, in another world, the first object hadn't happened, then the second object would not have happened either. So that's sort of the first step in our definition. So clearly that's a deterministic definition of causality, whereas we will take a probabilistic definition of causality. There's loads of really good films that are sort of based on this premise of this counterfactual event that sort of happens or doesn't happen. The example I always use, but it's getting a bit old now, is a film called Sliding Doors with Gwyneth Paltrow. I don't know if anyone's seen that. But essentially the premise is she either catches or misses a train, and the film sort of follows these two diverging timelines that actually in the end reconverge, of playing out those different alternative realities. So the probabilistic extension, if you like, of what Hume says. So if we stick with our A and Y, so if we intervene, so the way you have to think of causality is there's a sort of natural state of things, if you like, which Phil Davies calls the idle regime. But essentially, if we don't touch anything, so if we sort of leave the world alone, then that gives us like this idle regime, or corresponds to observational data. But if we intervene, and you can sort of imagine the hand of God comes in and flicks a switch or manipulates something in the real world. So if we intervene such that A definitely occurs, in an individual, you can think of this as in an individual or in a population, then Y happens with probability P. If we intervene such that A does not occur, so regardless of what happened in the real world, we switch that off for a person or for a population, then Y happens with probability Q, and then we'll say A causes Y if and only if P is not equal to Q. So it's straightforward enough and quite an intuitive definition. So as we manipulate this cause A, that changes the probability of the effect Y. So we won't dwell anymore on the philosophy of causality, but you can read a lot about that. So DAG, this slide's probably a bit basic for this audience. I'm sure we know what a DAG is. It's directed, or all arrows, all edges have arrows, so direction. And it's acyclic. We can't have cycles. Arrows represent flows of causation, as I said. One key thing that makes this a causal DAG is that if two variables in the DAG have a common cause, then that has to be included in the DAG. And you can kind of see why this is in this. So if we imagine this DAG represents some sort of truth, and again we'll come back to that later, then if I left out L, then I'm going to be in trouble. So if we have a common cause, we need to include it. However, other variables that might only cause one of the things in the DAG. So if there's a cause first, we said L was obesity, didn't we? So if we said diet only caused obesity and nothing else in this DAG, then it's fine to leave out diet. Although if we think diet causes cancer, which of course it does, then we should include diet. So I guess we've sort of already covered this a bit in terms of talking about time going from left to right. But a question that often sort of comes up when you show people these DAGs for the first time is, well, surely in reality we do have cycles. So if we think about L and A was obesity and metformin. So metformin is actually a drug that's often used in diabetes to control blood sugar in various ways, and is likely to have an impact on weight. So if we say, well, weight is going to cause the decision of whether or not metformin is prescribed, but once a patient is taking metformin, then that's also going to have an impact on weight. So we have a cycle, right? And that's not allowed. So how do we get out of this problem? So what we have to do, and this comes back to, again, time going from left to right, is we essentially have to unpack this graph longitudinally. So in this case, rather than just having one node representing weight and one node representing metformin, we have to unpack this in time. So we now have time 0, which is represented here by a subscript 0. So we have, if you like, weight at time 0 that causes whether or not metformin is prescribed at time 0. That metformin is not causing weight at time 0, it's causing weight at some future time 1. And that is then causing whether or not the metformin continues to be prescribed at time 1. So we'll come back to this a bit later. Things get quite complicated in these sorts of situations. Yeah. So what I'm trying to capture here, so the question was, can't you do this in two ways? So I presume you mean we could swap over the L's and A's in this graph. Yeah, so what I'm trying to capture here is that, if you like, the A0 is like, A0 plus epsilon, if you like. So I measure weight at time 0, and then very shortly after that, I make a decision about whether to prescribe the metformin. So I'm not prescribing the metformin and then not expecting that to have an instantaneous effect on weight. So that's why I've done it in this way. So yes, you can imagine this is A0 plus epsilon, which affects weight at time 1, which affects the decision at time 1 plus epsilon to prescribe metformin. Okay, but we leave off the plus epsilons. Yeah. So the question is it similar to a hidden Markov model? Well, I suppose, so often these graphs have a kind of Markovian property, but that would be an assumption in the causality. In this graph as it is now, so nothing is latent, everything is observed, but you can draw DAGs with latent variables as well. So yeah, there is a connection with hidden Markov models. Any other questions before we carry on? Okay, good. Yeah, please do keep asking great questions. Let's go back to the simpler DAG again. So we're just a bit of notation now. So we've defined causality, if you like, in terms of counterfactuals. So what would have happened if things had been different. So that expresses at an individual level the outcome Y that would have been observed if the exposure A, so this is sort of epidemiology language, we talk about exposures as the thing that we're manipulating, the thing that we're interested in the causal effect of, had the particular value little a. So, I think if I advance, yeah. So, I've written here, so there's a variety of ways to notate this, but one way is to do random variable y with a subscript a to represent the manipulation on the variable a. For clarity, you could write a equals a. So we write that, and the causal estimand, so the thing we're trying to estimate that we're interested in, is y subscript 1 minus y subscript 0. For example, we could also be interested in y1 over y0, or, you know, a log of y1 over 1 minus y1 divided by log of y0 over 1 minus y0, or whatever we like. So I've written y subscript a, which sometimes people use, although I realised later on in the slides that this was probably a bad choice because it clashed with other subscripts, but you can also superscript it, or it's quite common to put it in brackets as well. So there's different ways that people write this counterfactual notation. It doesn't really matter which one you use. So this is perhaps kind of an obvious point, but there's an obvious problem with trying to estimate y1 minus y0, and this is what we call the fundamental problem of causal inference. So for any individual, either a0, a equals 0, or a equals 1. So either they received the metformin or not. So if you like, so hopefully this sentence in the top right is okay. So when a equals little a, so if in the real world, in our idle intervention situation, the person received or didn't receive metformin represented subscript a, then y, the actual outcome, is equal to the counterfactual outcome had we intervened to set the intervention to its outcome that it really is. I hope that makes, it's kind of it's hard to say in a simple way, but hopefully it makes sense. So if really somebody didn't have metformin, and I propose an intervention that makes sure they don't get metformin, then we say that y equals y subscript a. That's not a tautology. That's an assumption, and it's an assumption that's sometimes called consistency. Oh, it's gone off again. And you can perhaps think a bit about why this is not an entirely trivial assumption, but we can make very little progress without making an assumption like this. But anyway, because of this fundamental problem of causal inference, it isn't possible sort of immediately to estimate y1 minus y0, because we can't sort of observe two worlds in which A happens and A doesn't happen and compare those outcomes. So the way we typically get around this is we take some sort of average over populations. So we talk about an average causal effect, the expectation of y1 minus y0 over some population, which of course is equal to the expectation of y1 minus the expectation of y0. And we can make progress now, but even then it's not entirely straightforward, because of course correlation is not causation, which here we would express by saying that the expectation of y under the intervention that sets a equal to 1 for everybody is not equal to the expectation of y given that a equals 1, which is in our sort of idle intervention of observed data. So hopefully that's kind of obvious, isn't it? We can't just look at everyone who received metformin and compare them with everyone that didn't receive metformin and believe that that tells us something about this causal effect. Yes, I realise I've been going for half an hour and I'm still on the very introductory stuff. So you're absolutely right, Magnus. It did sort of relax a bit too much. But anyway, I mean, it's important, getting these fundamentals is important, isn't it? Okay, so the obvious, if you like, way out of this is to use randomization, and this is why randomized controlled trials are so important. Because the reason, so in our simple DAG example here, the reason that the expectation of y sub 1 is not equal to the expectation of y given that a equals 1 is because we have this confounding by L. And we'll be a bit more precise about confounding as well in a minute. But if we conduct a randomized controlled trial, then of course we delete the arrow from L to A. That's what we mean. That's what it means to randomize. There's no incoming arrows to A. We toss a coin to decide whether or not somebody receives metformin or not. And that means formally that we have exchangeability between the people who receive, between the two arms of the clinical trial. And the way to write that is to say that the expectation of y sub 1 given a equals 1 is equal to the expectation of y1 given a equals 0. And if you think about what's happening there, so the first expectation is the first expectation is sort of the obvious one. That's saying in the treated arm, this is by consistency from the previous slide, this is just the expectation of y given a equals 1. The slightly trickier one is this second expectation. But there you can imagine that what's happening is we're saying, well, if we'd have swapped over the treatment and the control arm at the beginning of the trial, if we'd have arbitrarily decided that heads was control instead of heads was treatment, then in expectation, we would have observed the same result from the trial. So this is saying that, if we'd done that exercise, then these would be equal. And of course, if A either equals 1 or 0, and the expectation in those two partitions is the same, then of course that's the expectation of y1. And of course you can do the same thing with y0. And as I was saying, expectation of y1 given a equals 1, the first one, and expectation of y0 given a equals 0, we can get those straight from the data by consistency. And this line at the top that says that expectation of y1 given a equals 0 is the same as the expectation of y1 given a equals 1 is the step that we're going to use to... That's essentially what implicitly statisticians are doing when they work out causal effect estimates from randomized controlled trials. They're using this exchangeability that gives us that equality. So the other way to write that is that y subscript a is independent of A. So in other words, in the trial, if we'd intervened to either give people metformin or not, then that's independent of what actually happened in the trial. So it's sort of saying if we'd run the trial again and swap the arms over, then it's irrelevant what actually happened in the trial, which is called exchangeability, and is equivalent, if you like, to saying that there's no confounding, which is exactly what we believe about randomized controlled trials. Okay. And this last line is just sort of making clear that when we're doing causal inference, what we're doing essentially is we're starting from, so we have a causal estimand, this expectation of y subscript a. That's a sort of hypothetical or counterfactual thing. And we're then using our assumptions to link that with the real observed data. So this is our causal estimand. We can't estimate causal estimands because they rely on counterfactuals. We make assumptions about how these counterfactuals relate to the real world. And that gives us a, if you like, statistical estimand, this expectation of y given capital A equals small a. And as soon as we have those sorts of estimands, we can just use standard rules of probability, fit standard statistical or machine learning models to carry out the estimation. Just a quick note, just to make a link with, I don't know if people have ever read anything by Judea Pearl and various other people that talk about causal inference. So we sort of so Pearl has this thing called the ladder of causation, which is quite well known now in causal inference. So associations, this is, if you like, our idle intervention. We jumped straight here to counterfactuals because many people find this a natural way to talk about causal inference. But there's also this thing in between interventions. And the key distinction between counterfactuals and interventions is that for counterfactuals, we have to talk about what would have happened to an individual if things had been different. Whereas in the case of interventions, we're generally sort of only looking forward. So I'm now saying, right, for me today now, if I start taking metformin, then I have a certain risk. If I don't start taking metformin, then I have a certain risk. So there isn't any counterfactual in that. I either do or don't and can estimate either of those risks forward in time. And so if we're interested only in, if you like, interventions, then they're expressed only on population levels, really. So it would be something like the expectation of y or probability if it's binary given, and then Pearl uses this do operator, do capital A equals subscript A. I don't intend to go any more into the distinction between what we would, these sort of counterfactual operators that we were talking about and the do operators, because to all, for the sort of level we're talking about today, it doesn't make a huge amount of difference. But you'll see either of those notations and just be aware they do mean slightly different things, but it's subtle. Okay, so we did trials. So in observational data, of course, the treatment groups are not exchangeable. So the expectation of y1 given a equals 1 is not equal to the expectation of y1 given a equals 0. Because the people who actually receive metformin are different from the people that actually don't receive metformin. And if we believe this DAG at the top, they're different because of the confounding via L. However, what we do have, if we believe this DAG to be true, is what we call conditional exchangeability. So essentially we have exchangeability within levels of L. So if L is obesity, for simplicity you can imagine it's binary, someone is either obese or not. Then what we do have is if you look among the obese population, the ones that receive metformin and the ones that don't are exchangeable. And similarly, if you look among the non-obese population. As I say, that's under the assumption of this DAG, which is clearly an incorrect DAG. The reality is much more complicated than what this DAG says. So then we can write down the same sorts of equalities. We can swap a equals 1 for a equals 0 under this assumption of conditional exchangeability, or that y subscript a is independent of a given L. And that might be sort of familiar if you're used to reading off conditional exchangeabilities from DAGs. So the idea here is you ignore this arrow from A to Y because that's the causal arrow, and then you look for whether there's conditional exchangeabilities anywhere else. Okay, and that's the same as saying, if you like, that there's no unmeasured or residual confounding. Okay, so that gives us a way to proceed if we believe this DAG. And just to quickly show how we sort of manipulate these sorts of things so under that assumption, how do we get from being interested in the expectation of y subscript a to something that we really can estimate from data? Well, the trick with these sorts of things is to first of all use the law of total probability to expand this out. Basically expand this out over the confounders. So that's all the first line's doing. Nothing to do with causal inference there on the first line. The second line is using our assumption of conditional exchangeability to add in to that first expectation the a equals a bit. And we're allowed to do that because y subscript a is independent of a given L. So it's fine for us to just add that into the conditioning because it doesn't change anything because of the conditional independence. And why did we do that? Well, the reason we wanted to add that in is because once that there, we can use consistency, because now I have y subscript a, but I'm now conditioning on a equals little a. So I can use consistency because I'm looking in the population where my proposed intervention is the same as what really happened to those people. So under consistency, I can then change my y subscript a to just a normal y. So essentially these are the sort of tricks we're always trying to use in causal inference. So how do I get from a y subscript a, which is a counterfactual, to something that just depends on the actual data? And this is the sort of the most basic version of the standardization formula, or the G formula in causal inference. And there's much more complicated versions of this. And obviously, of course, this is a sum because we assumed here L was binary or categorical, but you just change that to an integral if L is continuous. And you'll probably need some sort of model, of course, then to make this all feasible, because essentially here we just count, to estimate these in the discrete case, it's easy, we can just count things, but we'll need a model as soon as things are continuous. Okay. So we talked there about confounding, and things with confounding are perhaps a bit more complicated than we made out. So if we have a diagram like this, then it's clear, everyone would just say L is a confounder, but we can build some more complicated DAGs where it becomes a bit less clear about what are confounders and what we do and don't need to adjust for, if you like, on our standardization formula, or however we want to do the estimation. So here the idea is that we talk about backdoor paths. So a backdoor path is essentially any path from exposure A to outcome Y that's a non-causal. So beginning by starting from A and then going against the flow of the arrows to start with. So here we just have a single backdoor path going from A to L to Y. And of course we have a single front door path going from A to Y. And to block a backdoor path, or a simple backdoor path from this we just condition on L. So in other words, in the standardization formula, we do this first step and work in subgroups of L. So we need to ensure that all backdoor paths are blocked to enable estimation of our causal effects. I'm not sure, so I'm guessing for this audience many people are familiar with these sorts of graph theoretic considerations. So collider, I guess people are familiar with the idea of colliders because it's a bit counterintuitive, but when you first come across them perhaps. But if you have a non-causal path like this one, A to S to Y, then this path is already blocked without conditioning on anything. So S is, if you like, a common descendant of both A and Y. So this is blocked when we don't condition on S. If you've never seen this sort of example before, then just to simply think through this, think about S being, so think, at home I have my lawn, it hasn't rained for a while, so if I cared about keeping my lawn beautiful, maybe I'd use a sprinkler, but I don't. But if we do, then if you might consider A is rain and Y is whether the sprinkler is on, and suppose that the sprinkler just comes on at random regardless of whether it's raining. So A and Y are actually independent. And then suppose that I make an observation of whether or not the grass is wet. So if I observe that the grass is wet, then if I know that it hasn't rained, then I know that the sprinkler must have been on. So that sort of induces, so by conditioning or observing something about S, I induce that relationship between A and Y. I guess many people have come across this sort of thing before, but you just have to watch out for these because they behave differently to other causal paths. So y is independent of A unconditionally, but y is not independent of A as soon as we condition on S. Mediators, so these are things, this isn't a backdoor path, there's A, M, Y, so you clearly don't want to condition on M if you're interested in the causal effect of A on Y, because M, if you like, is carrying part of or all of that causal effect. So in that case, we don't condition on M. That seems obvious, but as I say, pick an epidemiology or clinical paper at random and think about whether that mistake's been made. A reasonable chance of finding it. And yeah, I mean, we don't necessarily need to put these mediators in the DAG unless we're interested in what we call mediation analysis, where we really are trying to unpick the different, if you like, mechanisms through which the causal effect of A on Y is operating, which we won't go into here. That's a bit more tricky. And then this is quite a famous example. This is why I'm sort of trying to sort of talk about this. This is, if you like, the simplest example of where natural intuition breaks down. So in this example, so I should say in causal DAGs, we usually use U to denote unmeasured. So this means it's a variable that is unavailable to us, so it's not in our data set, but it is an actual variable that has causal effects on things. So we're interested in the causal effect of A on Y, and the question is, do I adjust for S or not? And the answer is no, we don't adjust for S. So if we adjust for S in this case, we will introduce bias. So the correct way to estimate A on Y is to do this without considering S. And to see why that is, if you follow the backdoor path, it goes from A to U1 to S to U2 to Y, but S is a collider, so at S, this backdoor path is already blocked. So if I condition on S, then I, if you like, open this backdoor path, which will bias the estimate. And I can't condition on U1 or U2 to block it again because they're not available to me. So the reason this example is talked about is because often when we're talking about confounders, we use the definition S is something, so S is a confounder here if S is associated with A, but is, if you like, upstream of A, and S is associated with Y. And then we say, if S is a confounder, then we should adjust for it. But here we can see that according to that definition, S is a confounder, because S is associated with A via the path S U1 to A. It's associated with Y because of the path S U2 to Y. But we shouldn't adjust for it because it's a collider, so adjusting for it opens the backdoor path that it's lying on. So that's why, that's just sort of saying, I mean, perhaps more for sort of epidemiologists and statisticians who are using these sort of non-causal definitions of confounding. Maybe you just want to think of it, I'll pause just for a minute so you can think about this. So if you can just have a quick look at this DAG and identify where the front door and back door paths are in this causal DAG and therefore what we need to adjust for. I don't know how far you got, but we better carry on because we're running out of time. So what are the paths? So we've got two front door paths, A to M to Y, and then directly from A to Y. So these ones are the front door paths that we don't want to block. We have A to S to Y, which is a path that needs blocking, but actually it's already blocked because it has a collider on the path. So as we said, conditioning on the collider S would open that path. And then we have just two standard backdoor paths, so A to L to Y, A, L, V, Y. And just one key point to mention on this is that to block these paths, we only need to block the path at one point. If you imagine a flow of water trying to get down this path, if I block it in one place, then that's it. The information doesn't get through. So here we only need to condition on L. That blocks both of those paths. We can condition on V, that's absolutely fine, but if we know that this is the causal structure, there's actually no need to condition on V. Okay, so that's the sort of structure of causal inference. Now, the obvious question is, besides writing down that simple standardization formula, how do we actually deal with the sort of, if you like, common situation, which is a variation of this DAG at the top, which looks simple, but of course L could be very high dimensional, which it often is in causal settings. So L could represent, images or something. It could be anything, that's sort of capturing that confounding. So how do we actually do this blocking of L, blocking this path A to L to Y? So essentially there are two, there's different ways to divide up these different approaches, but there are two approaches to do this. So approach number one would be the sort of approach that you'd probably be used to seeing, which is building a good outcome model including L. And the second approach that is, I suppose less sort of natural is to, one way of thinking about it is the idea is you want to try and change your data so that it looks like a randomized controlled trial, and then you know that you can analyze it in a simple way that you would for a randomized controlled trial. So outcome modeling approach, people with a background in machine learning, I'm sure this is no problem, so this is like the standardization formula before, essentially, that if we're interested in the expectation of Y subscript A, then we just do this double expectation. So the expectation of Y given A and L, and then we take the expectation of that over L. So that is basically exactly the same as the standardization formula that we had before. And the interesting thing with this strategy is if you're actually interested in conditional causal effects, so if you believe that the causal effect of A on Y differs between different levels of L, which is often something that we think and we might care about, personalizing treatments and things, if the metformin is good for people at some levels of L but not others, then of course we can estimate that just by dropping that outside expectation. And if you write down a linear regression, then this is just the beta coefficient, or if there's interactions in the linear regression, then it's just the beta coefficient plus the relevant interaction terms. And that's kind of obvious. Things are, of course, a bit more tricky for, basically any other kind of model that isn't a linear regression. So the other kind of way of doing this is to try and make things look like a randomized controlled trial. And in other words, rather than trying to adjust for L, what we're going to do is make some new data, like a pseudo population, where there isn't an arrow from L to A. So two ways of doing this. One is to use matching. So we start with all the treated individuals in our observational data, so the people who took metformin, and then essentially for each one of those treated individuals, we find an untreated individual who looks the same. In other words, they have the same or similar values of L. and then we match in that pairwise way. That's the basic idea. There's clearly lots of subtleties in that. So some of the subtleties are we could do many-to-one matching. We could recycle the untreated individuals to match to multiple people. And how do we deal with the scenario where we don't have exact matches? So we need some sort of distance function to decide what's a close match and what's not a close match. Which of course becomes like a bias variance trade-off. Just a key point that if we follow this kind of strategy is that we're actually estimating a different kind of causal effect to the one that we've talked about so far, because now we're building a population among people that looks like people who were actually treated in the population. So this isn't like what would happen if you treated the whole population. This is trying to capture what was the effect of treatment on the people who were actually treated. And arguably in many situations that's perhaps more of interest. And we call that often ATT, or the average effect of treatment among the treated. So it's just a slightly different definition of causal effect. And then the other way of achieving the same thing, so rather than matching, we can essentially re-weight people in the population. So that's like an inverse weighting scheme and is related to the idea of a propensity score. So the idea is that we essentially build a model for the probability of being treated given the variables L. Doesn't matter what kind of model you want to build, the logistic regression, or a deep learning model with many layers, or whatever you fancy. So as long as that model is sufficiently good, and we often call this model at the top a propensity score, so that's where the propensity score thing comes in. And then we can actually use this for in a few different ways. So as I say, one way, we could just use that directly for matching, so that's sort of like the previous slide. So rather than trying to match everybody on this whole complex space of L, we're now just matching on this simple space P of L. And you can show that that's okay, theoretically. You can put it straight into the outcome model, so rather than trying to build a model like the one from 2 slides ago, the expectation of y given a and L, we can instead build a model expectation of y given a and P of L. And again, theory shows that that's an okay thing to do. Or we can use an inverse weighting scheme. So we re-weight individuals. Well, if we want to estimate the average treatment effect among the treated, like the previous slides, we re-weight everyone by 1 over P of L. Or this slightly more complicated, so basically I've written it in terms of indicators, but essentially we're re-weighting treated people by 1 over P of L and untreated people by 1 over 1 minus P of L. So in other words, we're just inverse weighting everybody by the probability that they actually received the treatment that they really received. And as I was writing this slide, it reminded me that there's another important assumption that we need to think about in terms of being able to estimate causal effects from observational data, which is positivity. So this is a nice place to see why positivity is important. So positivity is saying that in our observational data, everyone has to have a non-zero probability of either being treated or not. And you can see quite obviously why things go very wrong with these calculations. If that doesn't happen, you get infinite weights. But yeah, so if you have a particular part of the population where everybody is treated or everybody is not treated, then it's very difficult to say anything about the causal effect in that particular strata of the population. Yeah. Yeah. Yeah, you're absolutely right. So Magnus's point is, so if P of L is very close to 0 or very close to 1, then you also have problems, and that's right. So then, if you like, if you're completely non-parametric about the way that you estimate these causal effects, then you're in trouble. So one way out is that you have some sort of parametric model and you extrapolate to those people from the neighbours. And that also helps you with the non-positivity, the total non-positivity that you were talking about, Magnus, where you'd say, so if say, I don't know, people under 40 never get prescribed metformin, then, if we sort of extrapolate from people just over 40 to what it might be like for them, then that sort of gets you out. Obviously, you're then making a strong assumption about extrapolation. Did you have a question? Oh, so I is that's just the an indicator variable. So so if A equals 1, that's 1. If A is not 1, then it's 0. People use different notations for that, I know. Yeah, I mean, so often the argument that people use about positivity is, an argument that I've sometimes heard is that, well, if nobody ever receives a particular treatment in a particular group, then that kind of suggests that the clinicians already know that it's a bad idea to give that treatment in that group. So therefore, it doesn't matter, we just forget about that group for estimating the causal effect. There's clearly problems with that sort of assumption, but if you think about it from a sort of decision theoretic perspective, it's sort of saying, well, if that's what the clinicians are doing, then they already have no doubt that it's a bad idea to prescribe, or we must prescribe in that group. But yeah. Yeah, lots of trust in clinicians. I'll just briefly mention, and this is where, so if you like to do some tricky maths, this is the topic for you. So the two approaches of, if you like, sort of reweighting kind of propensity idea and outcome models can be combined for an approach that then becomes doubly robust. And by doubly robust in that context, we mean that if either the outcome model that we built or the propensity model we built are correct, then the causal effect that we get at the end is valid, is unbiased. So that's quite a nice property that we have, so that we can have, that we take these two approaches. If either of those worked okay, and it doesn't matter which one it was, then our causal effect is correct. And the place where the interesting maths comes in, that I'm certainly not going to talk about because I don't really understand the maths, is an approach called targeted maximum likelihood estimation, which essentially uses the idea of incorporates both having an outcome model and a propensity model, but does so in a way that optimizes our estimation of the causal effect. So essentially the idea is saying that, well, often when if we're estimating all of these models, then I'm sort of spending my power, if you like, estimating nuisance parameters and parts of the model that are sort of orthogonal to my causal effect estimation. So what targeted, so the word targeted there is saying, well, if, basically I change the way I do my estimation so that I, target all my precision at the causal effect I'm interested in and don't waste it anywhere else. Please don't ask me any questions on this because I don't really understand it, but it's a good thing to look at if you're, if you enjoy the maths, because the derivations of this sort of thing, you have these so-called influence curves and things that tell you how you should optimize your estimation of different causal estimates. Okay, so I'll just, wow, we're already 3 minutes past 10. I'll say a bit about time-varying treatments. So suppose so this is the DAG that we had before, where we unpacked some sort of time, so time 0 and time 1. And suppose that now, instead of just being interested in a point intervention, we're now interested in this sustained intervention of continuing to prescribe metformin at time 0 and time 1 versus not prescribing it at either time 0 or time 1. So I'm interested in the strategy, if you like, 1-1 versus 0-0. And here's a question for you. So if I'm trying to build an outcome regression model for this, should we adjust for L1 or not? Yeah, I won't dwell on it too long because it's a trick question, of course. So the answer is, so the problem here is we're interested simultaneously in A0 and A1. If we look at A1, L1 is clearly so A1 to L1 to Y is a backdoor path in terms of A1. So that means we should adjust for L1. But if we look at A0, L1, Y is a front door path, which means we shouldn't adjust for L1. So that's sort of explained there. So basically, we have to simultaneously adjust and not adjust for L1 if we want to build an outcome regression model to estimate a causal effect of this nature, which of course we can't do. And this is why estimating these sort of sustained or longitudinal treatment effects is very challenging, because we can't just use our usual way of doing things and build models that are like Y given A0, A1, L0, L1. But as per a couple of slides ago, we do have some other tools in the toolbox. So if we go back to the standardization formula, which did end up, for the simple case, very much like an outcome regression. But if we sort of follow through the same steps where we developed that standardization formula for this same problem, then we can write down an estimator for estimating causal effects of this type. And the estimator looks like the one that's shown on the slide here. So essentially you have your outcome regression model. And I think I might have missed off L0 from... no, I think that's correct. So we have the sum over L1, but then we have to reweight on L1 given A0, and that's the way that we get out of this problem. So this is, if you like, a generalization of this standardization formula. Going through those steps that were in that derivation before will give you that formula rather than a standard outcome regression formula. So we just have this strange, so if you like, we're taking the expectations over L1 given A0 at the end. I'll have to check whether I feel like looking at that L0 should be conditioned on as well, but I don't have time to think that through in my head. But I'll check that and I'll correct the slide if it should have been there before it was circulated, before I circulate it. But the key point is that we can use this standardization formula, this G formula, to get us out of this problem. And we can also use a reweighting scheme as well. So the inverse probability weighting, we can also do that. And what we end up having to do is essentially weight according to a product of, if you like, the propensity score being prescribed being prescribed treatment at time 0. So probability that A0 equals 1 given L0, and then we have to multiply that by the weights that is, if you like, the propensity score of what got prescribed at time 1. And of course, this can all be generalized to multiple treatments. So I'm just showing 0 and 1 because it's much easier. But of course, you can have 0, 1, 2, 3, 4, 5, etc. So we can use inverse weighting or the G formula to get us out of this problem that outcome regression isn't going to work. And the name that's often used for this problem is treatment confounder feedback. So via L1 we have this treatment confounder feedback that essentially treatment at time 0 affects this sort of time-dependent confounder at L1, and that then affects treatment at time 1, and that's what causes our problem. Okay, so just quickly to show the generalization to multiple time points, which in principle works in the same way, but of course it gets a bit tricky to think about. And perhaps the other thing to say on this is that we've considered a very simple treatment policy there, so either don't treat at any time or treat at all times. We could also consider, again, it's more complicated, a dynamic treatment policy depending on L. So we could say, well, what if we treat, maybe start treating with metformin at time 0, and then if L is above 30 at time 1, then continue treatment, and if not, stop treatment. So we can evaluate the causal effects of those sorts of dynamic strategies as well. Okay, so that was kind of the end of the introduction to causal inference. I've left myself maybe 10 minutes to talk about the, the interesting extensions into prediction. All right, so why is causal inference useful in prediction? So, let's skip that one. So, the way that prediction models are used at the moment, normally, in terms of proposing an intervention, is based on the idea of what we call a risk approach to intervening. So, in the UK, and there's similar models in other countries, we have policies for primary prevention of cardiovascular disease. So you can go and see your doctor, you can have various risk factors measured for cardiovascular disease, so strokes and heart attacks. And in the UK, essentially the rule is that we calculate using this, a standard prediction model which is called Q-risk, the risk of bad cardiovascular outcomes. And the rule is that if that risk is over 10% over the next 10 years, so the probability of a cardiovascular event over the next 10 years is over 10%, then we should consider prescribing a statin. And a statin is a medication that lowers cholesterol. It's a very common and cheap medication that's very widely prescribed. So that's based, well, informally really, on the idea that those at higher risk have higher benefits. So we're essentially assuming that statins give a constant relative risk reduction to everybody. So therefore, if you have a high absolute risk of an event, then there'll be a high absolute reduction in your risk. Whereas if your starting risk is very low, then the benefit will also be low. And this graph is from this paper from 1995, so quite an old idea, that when risk is low, the benefit, which is this dashed line, is low. And for many drugs, you might approximately assume that the harm in taking that drug, whatever we mean by that, side effects or just the inconvenience or the cost of the drug, is constant. And what we're kind of thinking is that maybe 10% is about the point where the benefit starts to exceed the harm. But to be honest, we're probably giving too much credit to to where this guideline came from, but that was thought through in quite that way. So this approach so this isn't a causal approach, and the idea here is that, well, if we're interested in prescribing statins to individuals, then wouldn't it be better to calculate this in a causal way? So compare the risk of cardiovascular outcomes given prescribed a statin with the risk given not prescribed a statin. So this approach has many problems, which hopefully now we can see. So one, of course, is the assumption of homogeneity of risk. So on this relative scale, we're essentially assuming that the risk of assumption of homogeneity of risk reduction, I should say. So if anybody with a cardiovascular risk of 20% has the same roughly benefit of taking a statin. And the other problem is that the way these risk models always get interpreted, really, is that it's the risk, if you like, the treatment naive risk. So if I calculate someone's cardiovascular risk, it will be interpreted. So if I say your risk is 15%, then that's always interpreted as that's your risk if you do nothing and if we do nothing. So if you carry on with your bad diet and drinking alcohol and smoking, and we don't give you any medication to help you, your risk is 15%. These models were, of course, developed in historical cohorts with sort of no consideration of the longitudinal trajectories of these risk factors and treatments. So what this risk really means is if you behave similarly to what other people have behaved like in the past. So if people typically consider stopping smoking or improving the diet, and I would typically now give you a statin, then what we're actually calculating is your risk under all of these things. So the fundamental problem really is that it's very unclear. You don't think causally what these sorts of risks actually mean. And of course, beyond that, it's quite nice if we can work through, if we have a risk of a particular outcome, we can work through these what-if scenarios, which are, of course, causal questions. What if I stop smoking? As soon as we say what if, that's a causal query, which really, to answer correctly, we need to think in a causal way. When I mentioned the naive plug-in approach, I'm sure nobody in this room would make this mistake, but what many doctors do is, and I should say I don't blame them at all for this, it's entirely natural. What if I stop smoking? Well, in the calculator we put in smoker, so let's change it to ex-smoker, and that will tell us what will happen if you stop smoking. Which is, of course, not going to work, because these models weren't developed to have that sort of interpretation. But this is kind of the problem of, if you like, and as Magnus says, develop these models as well. We're guilty of sort of, basically we develop these models, we understand how they work and what they can and can't tell us, but then we basically just throw it over the fence and say, have fun with it, guys, and hope for the best. So as I was saying, this is just expanding out a bit on what's the challenge of talking about what the estimand is of the prediction model. What actually does a probability of 17% for an individual mean? So this is just giving a bit more detail on what we've discussed. So it's a problem because decisions are made on this calculated risk without really understanding what this calculated risk means. Skip that one. And the third motivation, this really corresponds again to what this estimand actually means. So what Q-risk tries to do, and what other models like this try to do, is we say, well, because this model is going to be used to look at whether people should initiate statins, we should definitely exclude everybody who doesn't take a statin, but that can only really be done at baseline if you don't think causally. So you need some causal thinking to be able to draw these sort of more complicated DAGs where time is unpacked, so that we can actually ask the question, what if this patient carried on not taking statins from now until 10 years into the future, because we're interested in 10-year risks. Okay, so combining causal inference and prediction, maybe I'll go on till 25 past or so, and that's okay. So how do we build these sorts of models? So Li Jing, who Magnus knows very well, led a review into this a couple of years ago, sort of looking at how people build these prediction under intervention models and what broad categories of methods get used. And here, by methods, I'm not really talking about statistics versus machine learning or anything like that. I'm just I'm talking at a sort of higher level of how people structure their way of thinking about this. So the simplest way to try and sort of get out of this problem is to try and think separately about, well, we want to be able to predict accurately in people, and we need causal effects. So you can sort of think of those as two separate problems. So the idea is that we get the causal effect from somewhere else, like a randomized controlled trial. So we know that the relative risk reduction of a statin, say, is 20%. And then we develop a prediction model, and then somehow we stick those two things together. And of course, there's a scale of how well that can be done. So the simplest way of doing it is that we just take our prediction model, assume that's treatment-naive risks, and then apply the 20% relative reduction to the absolute risk coming from the prediction model, which of course has all sorts of the problems that we described about what that prediction model really means. A slightly better way of doing this is what is now being called the offset approach, where essentially you include interventions as variables in your prediction model, whatever that prediction model is. But then rather than trying to estimate, so if we just think in terms of a simple regression model, rather than trying to estimate the coefficients of those treatment variables, we say, well, I'm going to use I'm going to drop in that coefficient as the one that comes from, say, a randomized controlled trial. So I have statins in my model, and I say, well, I know the relative risk reduction is 20%, so I'll just drop that in somehow. And the reason that's called the offset approach is because the way that you would achieve that is by handling the treatments as offsets in the model. So the usual place you come across offsets is in Poisson regression, where you offset the log of the population size. So now we offset, the treatment effect. Yeah, that's right. Yeah, so out the box, that's making the assumption that on some scale, it's a common treatment effect for everyone. But you could get around that by including the relevant interactions also into the offset. So I've never seen anyone try and do that, but I guess what you could do is have some trial data and build a model for the treatment effect conditional on covariates, and then basically offset that whole model in the prediction model. Yeah, I've never seen that though, but that would be quite cool. No, I've got a slide on that, I have time. And then the other approach is to try and do everything with the observational data. And there's quite a lot of literature on this. So Mihaela, who I think was here yesterday, has many papers on doing this sort of thing in various different ways. And that can either be done for point treatments or longitudinal treatments as well. So yeah, essentially point treatments is reasonably straightforward as long as you can assume that you know what all the confounders are. For longitudinal treatments, it's a bit more complicated, but you just have to sort of use the G methods that we spoke about, the G formula or the weighting schemes. Okay, let me just skip on a bit. I'll miss that one. Whether to talk about that. I'll miss that, but it's in the, I'll leave it in the slide deck. So this is about, well, maybe I'll mention it very briefly. So this is just about saying, well, the key question that everybody has is how do we actually validate a prediction model that's based on interventions? So normally for validating prediction models, we just look at, we have a validation data set, we know what the outcomes were, we can calculate our C statistic and calibration and whatever else we'd like to calculate. And that's all straightforward. But the problem with validating a prediction model where we're basically asking what if question, what if this patient took statins and what if they didn't, then we essentially want to validate against things that didn't actually happen, which is a bit problematic. There's a recent paper from Ruth Keogh and Nan Van Hellen that essentially covers how to do this using a sort of reweighting and artificial censoring approach. So the idea is that you use your data, restrict to patients that followed the treatment plan that you're actually interested in, but then reweight those patients so that they become representative of the original whole population. I'll leave this one as sort of the last slide, so it sort of partly answers what Magnus was just mentioning before about trials are probably too small to try and estimate a model for the treatment effect conditional on covariates. This relates to there's quite some work, really interesting work is going on, sort of trying to combine the strengths of observational and experimental data, because if you like, they kind of have complementary strengths, so this is such a natural thing to do. So observational data, typically very large, it's typically representative of the population that we're interested in, our target population, but it's typically messy, and we probably have lots of unmeasured confounding, making it very hard to estimate causal effects. Experimental data is, of course, normally quite small, but we have guarantees about unconfoundedness of treatment effects, so we can estimate causal effects, but typically not representative of our target population, and in fact, trials are normally, at least historically, conducted on highly selected populations, so we don't have the full range. So just to briefly say, there are a couple of interesting things going on here, I think. So, well, there's many interesting things going on, but I'll just mention a couple of my favourites. So, how can we combine these? So one is to think of this as a bias-variance trade-off problem, where you say, well, we know that trial effects are unbiased, but will typically, of course, have very high variance because of the small sample size, whereas observational data are biased, but will have low variance. So, usual sort of bias-variance trade-off idea that we can somehow combine them in an optimal way to minimise the mean squared error. I have to say my personal favourite in terms of cool ways of thinking about this is this second one, which is called experimental grounding. And the idea here is that you say, well, I could estimate my causal effects, if you like, my conditional causal effects on all the different covariates in my observational data, but I know they're biased. But I know that so if this is all my observational data all over this table, then maybe in one part I have a trial. So I can say, well, if I estimate that effect in the trial in this part, then I know that's unbiased. So I can kind of correct that part of my observational data. And then all I need to do is assume that I can somehow extrapolate that correction out to the rest of the observational data. And, arguably, of course, it's an assumption about extrapolation, but it's a much weaker extrapolation assumption than we would usually make. We're just assuming that in the sort of in the space of confounders that we haven't measured, we can somehow extrapolate some sort of parametric form for, the bias that unmeasured confounding causes. So that, to me, seemed quite interesting. I'd better more or less leave it there. I haven't talked about fairness or generalizability, but I could have done another hour and a half on those. Yeah, so I'll leave it there with the summary. So causal inference, incredibly, you have to be super careful. Prediction models are often used as if they were causally principled, but they aren't. And we're just beginning, I think, to really learn how to build and validate these models for prediction that incorporate causal inference. That's all, and I've just put in a few sort of key references that would be the useful ones to read in this space.
So I've noticed an interesting causal experiment is if you give speakers half an hour longer than they usually speak for, they all change their behavior, and every single one goes over time. So it's a kind of causal effect that's happening. But I think there's time for a few questions. So who's got a question? So while people are thinking, I've got a question about this last point about combining observational data and trials. I mean, that sounds really cool. Is that something that, is that happening already, or is that just something that people are thinking about? Are there methods already for doing that?
Yeah, there's quite a few groups thinking about how to do this. So yeah, so in terms of these,
the second one I was thinking about,
so this experimental grounding idea. I mean, there's been, to be honest, there's been a couple of papers on it, and it's one of the reason I highlighted it is because to me this is a really cool way of doing it and makes a lot more sense to me than just thinking of it as a bias variance trade-off. But it doesn't really seem to have caught on quite so much. There's a nice paper by, so in my references I gave like a summary paper. It's probably the last one on the list. So this paper by Colmet et al. Really nice and covers some of these topics.
Because one of the problem with trials, because I've worked briefly on trials recently, and trials are always just powered enough to get the signal you want, which is that something has an effect. So they're almost never powered for anything more subtle somehow. And so the observational data seems like a great way to expand, almost like you're matching, you can match the trial to the real data somehow. But yeah, cool if people are doing that.
Yeah. So it seems to be, I mean, it's a fairly new area. There's lots of sort of theory and methods papers coming out about this. I'm not aware of anyone sort of really doing this with dirty data, if you see what I mean.
Any other questions? Yeah? Let me just go to this.
Yeah, good question. Yeah, so I must say we haven't really yet managed to get these sort of causal thinking models into the NHS. The ones that we've successfully deployed have just been standard prediction models, typically based on, if you like, basic statistical models. So we've got some work ongoing now. So one of the projects that we're working on is essentially building like a variation of Q risk, so a model for cardiovascular risk prevention that does some of these things. So we're working on that now, and we've got some sort of pathways that could hopefully get that implemented into the NHS. I think things have changed a lot, even over the last few months, I think, in terms of how prepared healthcare would be for more advanced AI models. Outside of imaging, where it seems to be quite accepted, but in fields like where I typically work using sort of structured electronic health record data, there's still been a lot of resistance to anything more advanced than like a simple logistic regression, where the clinicians can look at what the input variables were and what the odds ratios are and agree that it makes sense. But yeah, I think that's potentially changing quite fast now. I probably rambled a bit, but hopefully that answers the question.
Okay. I think maybe we should break for coffee. So if anyone has any more questions, Matt's here, so grab him over coffee and ask him about causal stuff. Let's thank Matt once more.